Hello everyone. Today we'll discuss about continuing our previous topic. Now this time we have stereoisomerism in coordination compound. We have already discussed structural isomerism in coordination compounds, and now this time we'll discuss stereoisomerism. The word stereo is related to space. In case of stereoisomerism, the two compounds having same molecular formula, but they differ in terms of the spatial arrangement of their atoms or group of atoms around the central atom. Now, the two categories in this case are geometrical isomerism and optical isomerism. Let's discuss in detail first geometrical isomerism, which is commonly also known as cis-trans isomerism. We know in case of coordination complexes, the most common example we study at +2 level is the two coordination numbers. First case is ML4 type, ML6 type, that is coordination number 4 and coordination number 6. This will be the case if L is the monodentate ligand. Otherwise we also have examples of bidentate ligands also. Now in case of ML4 type, we have further two cases, complexes tetrahedral as well as square planar complexes. Now it's very important that in case of geometrical isomerism, for example, A and B are the two geometrical isomers of each other, then when we change some spatial position of atoms or group of atoms around the central atom in A to create B, then B will be called its geometrical isomerism only if the nearest environment of any particular ligand is changed in the space. If the nearest environment is not changed, that means nothing new is created in the space, it will not be a geometrical isomerism, it will be the same molecule. Fine. Now let's take the case of tetrahedral complexes and see whether geometrical isomerism is possible in this case or not. This is a complex ML4 type. I have taken all the four ligands are different, L1, L2, L3 and L4. We know in case of tetrahedral all the bond angles are 109.5. That means it's a highly symmetrical structure. Clear? Now let me try to create whether changing position of one of the ligand will create something new in the space or not. I have changed the position of L1 with L4. Now in the present case, before changing the position, let's say the L1 is in the nearest environment of L2, L3 and L4. What is the nearest environment? Means the nearest bond angle which is around that particular ligand. Some other ligands which are at the nearest bond angle to it. Because all the bond angles are same, so L2, L3 and L4 all are at the same bond angle to L1. So all come in the nearest environment. Fine. Now here I have changed the position of L1 with L4. In this case, L1, further if you examine, all the bond angles are same, that is 109.5. So here also the nearest environment of L1 is L2, L3 and L4. So as we have observed, in this case, in case of tetrahedral, we have changed the position of one of the ligand, right? But none of the ligand have changed their environment in space. So that means geometrical isomerism is not possible in case of tetrahedral complexes. Now we are left only with square planar and octahedral complexes. The other case, that is ML6, is the case of octahedral complexes. Now in case of square planar complexes, let's examine in this case the structure in which only one type of bond angle is there. Just like in the case of tetrahedral, geometrical isomerism will not exist. But here you have two type of bond angles. If you observe here, this angle is 90, fine, but this angle is 180. So because two type of bond angles are there, now in this case if you change the position of ligand, that we'll observe later, there will be changes in the spatial environment and new isomer will be created. Similarly, in case of octahedral complexes also, you have more than one type of bond angles here. Like that, this is the vertical 90 degree, this is 90 degree, while this angle is 180 degree. So again in this case also, we have different positions, right? So different bond angles, so geometrical isomerism is possible. So you got a very important question in exam here, that why geometrical isomerism is not possible in case of tetrahedral complexes, right? So now one by one we will discuss geometrical isomerism in different complexes. Let me take the first example, geometrical isomerism in ML4, that is square planar complexes. Now here you got some categories. First class is MA2B2 type. Second, it is AB A type. Just wait, I'm sorry. We have another example here, MABC2 type. The third example we have here is MAB twice, and one more, it is MABCD type. Fine. Now I have to tell here, A, B, C, when they are written alone, they are certain monodentate ligands. Fine. And AB written in bracket, this is together, this is considered as one ligand. AB is a bidentate ligand. But as it is mentioned in AB, that means this is such type of bidentate ligand in which the two donor atoms are different. Fine. So this is the case in which we'll discuss these four cases with proper examples in which geometrical isomerism, that is cis-trans isomerism, will exist. Fine. So let me start with the first category here, MA2B2 type. MA2B2 type. We have here example of platinum, very important complex here. This is the complex of platinum. Now here let me draw its square planar structure. Fine. Now one of the spatial arrangement of ligands is this. Now in this type of arrangement, the closest position of the same donor atom is moved. Nitrogen, chlorine, chlorine on the same side. So such a isomer is called cis isomer. This particular isomer of this compound is also known as cisplatin, and it is very much commonly used, very important in the treatment of cancer. Another, if I just make some changes in the position here, suppose Cl here, I have replaced this ammonia with Cl, these are exchanged, so you have got this type of arrangement here.